We're going to look at what causes the phases of the moon. Now, the moon's phases are caused by the varying light and shadows cast by the sun on the moon as it moves in its orbit around the Earth. As we learn about this, we'll come to realize that the phases of the moon are largely dependent upon the location of the moon in its orbit around the Earth. Now, to help us understand this, we're going to spend a lot of time looking at a model of the moon phases. Now, in science, we use models for all kinds of things, and one purpose is to help explain and to understand how something is caused. We're going to use a model of the moon at various locations in its motion or orbit around the Earth. As we look at this model, it's important to recognize that we are taking the perspective of someone floating above the North Pole of the Earth and watching the moon as it moves counterclockwise in its orbit around the Earth. Now, in this model, we're basically looking at 8 different snapshots of the moon in its motion. Now, each of these snapshots will represent one of the 8 major phases of the moon. Now, this entire motion takes 28.5 days. So on this model, it would move, for example, from location 1 all the way around counterclockwise and back to location 1 in 28.5 days. It's also important to note that the numbers in this model are only there to facilitate the explanation of the model. It's also important to recognize that the sun in this model is a very long ways away. In real life, the average distance from the Earth to the sun is 93 million miles, or 150 million kilometers away. And so in this model, we represent the light from the sun coming in as parallel lines. This is important to note because when we are so far away from a point source of light, the light essentially arrives parallel. Now, as we look at this model, we will determine the phases of the moon based on an Earth-bound observer's perspective. What that means for this explanation is we will imagine that we are standing as a person on the Earth directly below the moon in question. And we'll take their perspective, for example, their right side and their left side, to help us identify which phase we're looking at. Let's look at our model a little more deeply by looking at an example. Let's take moon number 3. Now, this moon is the location where we have a first quarter moon. We'll discuss some tips and some processes that will help us to be able to identify the moon phase at every location. An important thing to know about this model is that we have a single point source, or the sun. And whenever there's a single point source, it can only light up half of an object at any time. So in this location number 3, only the half of the moon that is facing the sun can be lit up, and the other half will be shaded or will be in darkness. The same is true for every moon in this model. So we're going to apply this shading to all of the moons and use this throughout the rest of this model. An important part of using this model is knowing which parts of each moon at each location are lit up. And that's always going to be the half that's facing the sun will be lit up, and the half facing away from the sun will be dark. The same is true for the Earth. The side facing the sun will be lit up, and the side away from the sun will be dark. Now, it's also important to recognize in this model that when you look at an object, for example my body, you can only see a half of it at any time. In this case, the front half. The same is true with all of the moons in this model. An Earth-bound observer can only see the half of the moon that is facing the Earth at any time. Now, it is the mix of these two halves, the half that is facing the sun and is therefore lit up, and the half that we can see from the Earth, that cause the variations and the different looks of all of the moon phases. So as we look at the moon in location 3, we have the half that's lit up and the half that's been shaded for darkness. We also have the half that's facing the Earth, which is visible from the Earth, and the half that's not visible from the Earth. And from this, as we imagine the perspective of standing on the Earth looking at this moon, we can see and imagine what this would look like. As we look at location 3, we can see that it is a first quarter moon. Now, we can see why this is called a quarter if we remember that we can only see half of the moon at any one time. So if half of the half that we can see is lit up, that is a quarter. Now we can tell that this is a first quarter moon instead of a third quarter moon. If the light is on the right, this means it's a waxing moon, or it's at the beginning of the phases of the moon. If the light is on the left, it is at the end of the phases of the moon, or is a waning moon. So since the light is on the right, we know that it's in the first half of the moon phases, and it's a first quarter moon. If it were opposite that and the light were on the left side of the moon, This would be a third quarter moon, or also called a last quarter moon. Let's look at location number 4 as another example. And as we do this, it's important to remember the 3 things that help us identify the moon phases. The first is that the side of the moon facing the sun is always going to be lit up, and the side away from the sun is always going to be dark. The second is that from an earthbound observer's perspective, we can only see the half of the moon that is facing us. There's no way that we can see the back half of the moon. Third thing to remember is that it helps to look at and describe what the moon would look like to help us identify the name and the shape and look of the moon from an earthbound observer's perspective. So as we look at location 4, we've remembered to shade part of the moon away from the sun dark and leave the part that is facing the sun in light. We also can add an additional line to help us recognize which part of the moon is visible from the Earth and which cannot be seen. As an earthbound observer would look at this moon, they would see light on the right-hand side and dark on the left-hand side. They would also see that there's more light than a quarter moon, but less than a full moon, which makes this a gibbous. So since the light is on the right, and since it's a gibbous, we know that it's a waxing gibbous moon. Let's look at another example. How about location number 8? Again, we're going to look at our 3 key points to identify what moon phase this is. Again, first we're going to remember that only half of the moon can be lit up, and it's going to be the half that's facing the sun. The other half, the half facing away from the sun, is going to be dark, and so we've shaded that on the model. The second thing we're going to remember is that from an earthbound observer's perspective, they can only see the half of the moon that's facing the Earth. And again, it helps us to draw a line on this model to identify which half is visible from the Earth. Now our third tip again is describing what that would look like to an earthbound observer's perspective. Now as we look at this moon, we can see that there would be light on the left-hand side, but that it's going to be less than a quarter moon's worth of light. That tells us that it is a crescent moon. And since the light is on the left, that tells us it is a waning moon. So here in location 8, we have a waning crescent. There are also a few other things that are important to remember about this model. We can see these by looking at location 1 and location 5. Now it may appear at these locations that the shadow from the moon would fall on the Earth, or that the shadow from the Earth would fall on the moon. Now typically this is not what happens during our moon phases. These are rare situations where these shadows overlap, which are called eclipses. And these are not what's happening in this model. For example, if we look at location number 5, we can see that the Earth's shadow, if they were overlapping, should black out the entire moon. But location 5 is actually a full moon. There are no shadows on this moon. It's important to recognize that most of the time, the Earth and the moon are slightly above or slightly below each other so that their shadows do not overlap. Only when they're perfectly in line with the sun do we have them overlapping, and we have eclipses, either lunar eclipses or solar eclipses. Now practice using this model so that you can be able to identify the moon phase at every location. It's important to remember the 3 things that we've talked about multiple times. First, that only half of the moon or any object can be lit up by the sun at any one time. Second, that only half of the moon or the half facing the Earth is visible from an earthbound observer's perspective. And third, it's helpful to describe what we would see as an earthbound observer and then figure out the moon phase from there. Now this model can actually show us a lot more than just the location of the moon to cause each of the moon phases. It can also give us information about when we would be able to see each of the moon phases. As we've talked about before, and as we've shaded on each of our moons, we can see where the sunlight hits and where the sun cannot hit on each of the moons. And we've shaded that in on each of our moons in this model. Well, the same is true for the Earth. We can shadow the dark part or the night on the Earth as well. And doing this gives us more information about which moon phases would be seen at what time of day or night. Now, it is a common misconception that the moon is only visible at night or that it's mostly visible at night. The truth is the moon is visible just as much during the day as it is at night, but that we see different phases during different times of the day or the night. Now, once we draw the shadow on the Earth, it shows us where the daytime is and the nighttime is. We can also add a few additional points on our Earth to help us identify specific times of day. For example, if we have the terminator, which is the break between day and night, we can label that as sunrise or sunset. Now in this model, we're going to label that as 6 a.m. and 6 p.m., even though that might vary throughout the different times of the year. Now halfway between 6 a.m. and 6 p.m. is noon, and halfway between 6 p.m. and 6 a.m. is midnight. And if we add these additional points to our model, we can begin to identify when we would see these different moon phases. For example, if we look at location 1, which is the new moon, we can see that it should be directly overhead at noon in the middle of the day. Let's take a look at the opposite. Location number 5, which is the full moon. We can see that this moon should be directly overhead at midnight. We can do this with any of the moon phases. For example, if you look at a waxing crescent, we can see it should be directly overhead between noon and 6 p.m. or 3 p.m. We can also look at things like a first quarter moon. Now this should be visible partly during the day and partly at night. And we can go through each of these moon phases and identify when they should be visible and when would be the best time to see them. So again, we can see that this model not only shows us and helps us identify what moon phase is at what location of the moon's orbit around the Earth, but we can also identify when is the best time to see that moon phase.